basically, we just went over the first data set that tells you the autocorrelation of daily returns. They are very close to zero. And this is one of the most important data sets about the financial market asset returns, okay? Because the significance is just so big. It just tells you that, very hard for you to beat the market because it's very hard for you to predict tomorrow based on the information of today, okay? So, and then we are going to have some other data sets that go over them one by one, but I'm not going to spend as much time as on each one of them because, okay, we are going to go over them, okay? So the second data set tells you that the unconditional distribution of the daily returns have fatter tail than the normal distribution. Okay, fatter tail meaning, okay, let me show you what that means. So this is figure 1.2. This is the histogram of the daily return for this 10-year period. And then the bell-shaped curve indicated by the right line is the normal distribution line. Okay, as you can see that the middle portion of the data align roughly well with the normal distribution. But if you take a look at the two tails of this distribution, especially the left tail, okay, you can see when, for the daily return, the normal distribution would tell you that, okay, it's very hard, very rare to see a return as negative as 4% per day, 5% per day, 6% per day, 7% per day. But the bars here tells you that they are actually much more frequently happening than suggested by the normal distribution. Okay, so this is what we meant by the fatter tail in the financial market. Okay, there are a lot of fancy terms, fancy words to describe those events. Okay, fatter tail is the more academic way of saying it. Okay, in the financial newspaper, financial media, we sometimes call those of the black swan events. Okay, or the tail events. Okay, all of those events meaning something that is beyond what the normal distribution can capture. Okay, for example, the Black Friday event I just talked about, S&P declined by 22% in October of 1987. On a particular day, it declined by 22%. That's gonna be, if you kind of extrapolate this, it's gonna be here, okay? Basically, those events are happening very, very frequently. And the last, and then, in the past 15 years, we know the US stock market is doing extremely well, okay, doing extremely well. And then in my memory, because I'm actually invested during this period, so I know very well on which days the market is not doing well. So one of those days is basically March of 2020, okay? March of 2020, we have 4 days the returns are worse or more negative than 7%. Okay, that gives rise to a 1/3 decline in March of 2020, and that's basically very high frequency. Okay, in 1 month, you see 4 days market tanks by more than 7%, and then another more scary episode that was gonna be last April. Okay, so basically, I think last April wasn't that scary because the S&P declined by a total of no more than 20%, and they quickly kind of reversed after the tariff news. The tariffs kind of removed, but we do have a few days the market tanked by more than 5%. Okay, and then similarly, okay, the market not only sometimes doing very poorly than imagined, sometimes they are doing abnormally well, okay, extremely well. So on some days the market can go up by 6%, 7%, or even 10%, okay? And the interesting thing is, actually, the very big downward movement, they actually oftentimes go hand in hand with the very big upward movement. Okay, those kind of events more often happen when the market is panicking. Okay, so basically on one day, investors hear about some very negative news, they all sell. Okay, push down the price, and then on the second day they realize, okay, maybe we were overreacting, maybe we should buy back some of the shares. Then they all push into the market and buy the shares, then the price will go back. Okay, so basically this histogram tells you that the S&P 500 or for the equity market, the daily return does not follow exactly a normal distribution. The tails are fatter than implied or suggested by the normal distribution. This is our status effect number 2. And we sometimes formally call this non-normality. Okay, non-normality. And in the first week of the lecture after the spring break, we are going to talk about more formal tools to capture such non-normality. Okay, and then status effect number 3 tells you that the stock market exhibits occasional very large drops, but not equally large up moves. Okay, basically, even though there are large moves, but in terms of the size or in terms of the frequency, the very large drops are more frequent. Okay, more frequent, and therefore the return distribution is negatively skewed. Okay, negatively skewed. Basically, it's skewed more towards the negative side. Okay, it's not purely a symmetric distribution. Okay, the status effect number 4 says that the deviation of the returns completely dominates the mean of the returns at short horizons like daily. Okay, if we actually take a look at the data, okay, let's quickly take a look at the mean and the standard deviation of the S&P 500 during this decade. Okay, let's take a look at the mean of the return. We can see it's very close to 0, right? Because the mean of the return, the E negative 0.5, negative 0.05, it basically means up to the 5 decimals. Okay, up to the 5 decimals. It's a very small number. And if you take a look at the SD, okay, this is basically the standard deviation of the return is a lot larger. So it's 0.0137. Okay, so typically when we are talking about very small numbers, we are using a term called basis points. Have you guys heard about this, or have you guys used this before? Basically, what is 1 basis point? 1% of a 1%, right? So this is more commonly used in the fixed income market because the magnitudes are relatively small. Okay, so now if we take a look at the mean return and the standard deviation, let's talk about them all. Represented them in terms of basis points. So how large is the mean return in terms of basis points? Is about 0.5 basis points, right? Because 1 basis point is like it's basically this. Okay, and that mean is 5586, right? It's this. 5586. Okay, so basically you can see the mean return is roughly speaking half of a basis point, whereas the standard deviation is 138 basis points. If you do the comparison, you basically realize that okay, at the daily frequency, in terms of basis points, is all the attention is devoted to the standard deviation. The mean is so close to 0. Okay, not even 1 basis point, but the standard deviation is very big relative to the mean. Okay, and then you may ask, oh, this doesn't seem to be aligning very well with my intuition because I know I wanted to put money in the S&P 500 because I know over time it's going to deliver me returns. Now you tell me the return is close to 0. So why is that the case? Because we are looking at the daily returns. Okay, we know S&P 500 can give you or can deliver a return in the neighborhood of 10%, okay, per year. But if you divide that 10% per year by 250, that's the number you get. Okay, that's the number you get. So basically, again, everything is still right. Okay, you just have to reconcile the different pieces of information with yourself. The bottom line we get from this data effect is that at the high frequency, like daily, the mean can just be taken to be 0. Okay, because it is so close to 0. Whereas the volatility is what matters in terms of magnitude. Okay, and that actually laid the foundation for a lot of our future work, because in the future, when we are trying to model returns, we only focus our attention on modeling the volatility. We are not going to model the mean, because we are going to take the mean to be 0. Okay, and we are going to focus our attention purely modeling the volatility. And this data effect number 5 tells you that the variance of the daily returns, if you measure that using the squared returns, okay, actually they exhibit positive autocorrelation with its own path. Okay, so basically let's take a look at the figure. Okay, this is figure 1.3. So this is the autocorrelation of return square estimated from this 10 years of data. Okay, you can see this is very different from the autocorrelation of returns, in the sense that the autocorrelation, they are actually mildly positive. You can see for the first couple of legs, they are mildly positive. They are in the neighborhood of 30%. Okay, 30% correlation or 0.3 correlation. That is already called weakly positive correlation. Okay, meaning how to interpret weakly positive correlation? Meaning that if you see today the variance is high, there is a high chance, okay, tomorrow's variance will also be high. Okay, so basically when the market is volatile, when the market is panicking, okay, the panic will not go away immediately. Okay, when the market is panicking, it's gonna panicking for a few days. That's why, okay, when you see today high volatility, tomorrow there is gonna be a high chance it's also gonna be volatile. Okay, that's basically exhibited in this kind of figure. And of course, we can very quickly. Oh, you have a question?
Is this only for squared returns?
For squared returns?
Only for that?
Well, squared return is a proxy for variance. Okay, so in the maybe in a few lectures we are going to have better proxies for volatility. then that's going to be a better measure for risk. So here we are just using return square as a proxy for the variance, because return square is indeed a very good proxy for variance. But the variance is different from volatility. But variance is also one form of risk. Okay, so we can actually very quickly reproduce this figure based on the code we have. Okay, you can see that based on the code, I just have to copy and paste everything I have written up there. Okay, copy and paste here. I only need to change the variable from return to return square. And return square is defined here. Okay, return square is calculated as RET square. And then let's make the plot. Okay, you can see this is exactly the same plot as we saw on the slide. Okay, the interpretation here is that even though returns are very hard to predict, almost impossible to predict, but return square are easier to predict. Okay, are easier to predict. So that's kind of like, very interesting. Okay, very interesting. Then the next data effect is equity and equity index. They exhibit negative correlation between variances and the returns. Okay, so what this means is that oftentimes in the market, okay, when you see return declines and then you will see the volatility or the risk go up. Okay, that is very common, right? So sometimes because of risk going up, and then the return will decline, and that's what we mean by the negative correlation between variance and the returns. And economists give this actually they come up with a story to describe this relation. Okay, they call this the leverage effect. Okay, so right now I will not talk too much about it. Okay, you guys all you need to know is okay, the negative correlation happening very often in the market between variance and returns is termed by economists as leverage effect. And in one lecture I will talk to you very much more detail about why this is called leverage effect. Okay? And Stellar effect number 7 tells you that the correlation between assets, okay, if you are moving from one asset to multiple assets, okay, let's say you are looking at the correlation between stock and bonds, okay, the correlation are not fixed, they are actually time variant. So sometimes stock and bonds may exhibit positive correlation, and sometimes they exhibit close to zero correlation, and sometimes they exhibit negative correlation. Okay, so we are going to discuss this. We're going to discuss models or tools to be able to capture this phenomenon in chapter 7. Okay, in chapter 7. And then standard effect number 8 tells you that even after standardizing returns by a time-varying volatility measure, which we will be learning, okay, in some of the lectures, and they still have fatter than normal tails. We refer to this as evidence of conditional normality. Okay, if you don't know, if you feel like okay the term is kind of new, I don't capture it, it is fine. Okay, so all of those Stellar effects, as you can see, we just covered. Okay, I'm only talking in very much detail about the first Stellar effect. For all the others, I'm just going over them. Okay, all of those Stellar effects represent a guide. Okay, represent a roadmap for us to cover in the future lectures and future chapters, because every one of those Stellar effects will represent one aspect of the market that we will have to learn tools to be able to capture them. Okay, and then the next one is as the return horizon increases. For example, when you are moving from the daily return to weekly return to monthly return to quarterly return to semi-annual and the annual return, sometimes even 3-year, 5-year, okay? And then the unconditional return distribution will become more and more like a normal distribution. More and more like a normal distribution. So basically, the distribution of the return will change as the return horizon increases. Okay, as the return horizon increases. Of course, this matters for what we are doing, right? Because for risk management, especially for places like banks, commercial banks, and insurance companies, because all the transactions have to be executed overnight. So a lot of the risk management is done on a daily basis. And of course, that is for regulation purposes as well. Okay, but if you are a portfolio manager, you are mainly managing portfolio assets for people under retirement. Okay, and then their return horizon will be very long, maybe 10 years, 3 years, 5 years. If that is the case, then you don't have to worry that much about the tail events or the factor tail in the market, because it's going to look more and more like a normal distribution. Okay, so that is basically the list of Stellar effects we wanted to talk about regarding the asset market. Again, some of the Stellar effects are more important than others. That's why I'm putting more attention, spending more time on it. But all of those Stellar effects just a different aspect, different dimension of the market that in the future chapters, in the future weeks, we are going to cover each one of them respectively. Okay, so you will see those things, and once again in the future chapters. Okay.
Just one comment is like when you go in a time horizon widely, then it looks like normal distribution. Somewhat it reminds me similar like in physics, like a Newton law versus a quantum mechanics. Like if you really like magnify into it's a totally different world.
Right. It could be. There might be some kind of parallel going on between finance and physics. Okay, so now let's move on to the next part of the lecture. Okay, so we are going to talk about a generic model of asset returns. Okay, a generic model of asset returns. So let me basically first show you how that model is, what that model is, and then I will simplify the model and show you how to use it in the future. So it's called a generic model. Of asset return. Basically, the model we are going to be talking about is something that is very generic. Okay, so basically in the future we are going to be using this model frequently to model returns. The model is written like this. Okay, RT plus 1 equal to mu t plus 1 plus sigma t plus 1 times Vt plus 1. Okay, let me explain each one of them here. Okay, so of course the left-hand side variable is RT plus 1. It's basically the log return we are trying to model. Okay, it's the log return we are trying to model. And then the mu t plus 1 here is called the conditional mean. Conditional mean of the return. So why we call that conditional mean? Because when you are using this model, you can see there is a time indicator there. Okay, so basically the conditional mean is your forecast based on all the information you know up to time t. Okay, that's your expectation regarding the mean of the returns for day t plus 1. Okay, and of course, because we just learned that daily returns, the mean is very close to 0. Okay, so therefore this is going to be taken to be 0 in a lot of the applications. Okay, so we can actually get rid of it from this, even though we know this is daily called conditional mean, but because it's very close to 0, so we can get rid of it. Okay, and then this sigma t plus 1 is the conditional volatility. Okay, so that variable is something we are going to spend a lot of time modeling it. Okay, we're going to be learn some models to model this term, because we know for daily returns the mean is very close to 0. So therefore, if you want to model it, all the attention should be devoted to model the volatility. Okay, and then this Vt plus 1 is a term has many names. Okay, they all mean the same thing. Okay, oftentimes it's called the shock. Okay, it's basically something regarding tomorrow that we don't know. Okay, so we do have our best forecast for the volatility, but even though we know the volatility, still we don't know the precise value of the return, because that is something not under our control. It's something not baked into our informational site. So therefore, it's called a shock. Okay, something that cannot be expected. Okay, so and this shock oftentimes is modeled by a standard normal, distribution N01. N01 meaning a standard normal distribution with a mean of 0 and a standard deviation equal to 1. Okay, so you can see that IID, actually it's N01. Okay, so IID basically meaning the shocks are identical and independently distributed as the normal distribution. Okay, so this is basically the generic model we are going to be working with in many of our applications in the future. Okay, so the next thing is something we are going to be, it's a very handy model, okay, exactly related to the generic model. Okay, to model the returns, okay, to model the returns I just mentioned, all your attention should be devoted to model the volatility. Because if you wanted to have observations, or potential observations of the returns for the future, right? If you know the volatility and you can just using the random number generate to simulate a few observations for the shock, you can just take the product of them, you will get a potential realization for the return. Okay, so therefore the next thing you gotta do is to, okay, what about a model for volatility? Okay, what about a model for volatility? So we are going to learn very quickly, okay, a model that is very popularly used in practice, okay, in practice. And this model is actually proposed by a research team in JP Morgan, okay, in JP Morgan. And this model is called the risk matrix model, okay, risk matrix model. So the volatility, so the model basically written like this, okay, written like this. So basically, the risk matrix model says tomorrow's volatility, sigma t plus 1 is the left-hand side variable for the risk matrix model. It tells you that your forecast, okay, for tomorrow's volatility square should come from two sources of information, okay? One source is today's volatility square. Okay, another source is the market return for today. Okay, you can say RT is basically the return just realized in the market today. Okay, you basically take the return square and then take the volatility today, you take the square, and then you take a weighted average. Okay, that's gonna give you your forecast for the volatility of tomorrow. Okay, that's gonna give you the forecast for the volatility tomorrow. And then most importantly, the 94 and the 6%, those two weights, okay, they add up to be 100%, meaning that you are not losing any information by doing the weighted average. And you may ask, okay, you may ask, where do you get the numbers? Where do you get the 94% and 6%? Okay, so that's where the JP Morgan comes in. Okay, so basically they come up with a model, okay, with a parameter that is unknown. So basically the original model looks like this. Equal to lambda sigma t squared plus 1 minus lambda RT squared. Okay, so basically there is a parameter lambda to estimate. And then the research team at JP Morgan, they actually estimate that model based on wide range of assets. They find, okay, it turns out that for a wide range of assets, if you are looking at the daily data, the lambda will be around 94%. Okay, then you know, in the future, in practice, okay, you know, we just use lambda equal to 94. Basically, this will be the version of the risk matrix model that we use to model or forecast the volatility for tomorrow. Okay, you can see that there is a very important word I'm using here that's called forecast. Okay. Okay. Whenever we use the word forecast, okay, it has special meanings. Okay, forecast basically means that all the inputs you use in your forecast can only be the information you know by the time you are making the forecast. Okay, so basically when you are using the risk matrix model, you are basically at the end of day T, right? You are making the forecast for tomorrow's volatility. Therefore, all the information showing up on the right hand side of this equation must be the information you know up until now, up until when you are making the forecast. Okay, take a look at the RT. Okay, that's exactly what is realized in the market today. You know it by the time you make the forecast. And sigma t, that is the volatility for the return for today. Okay, and you should know that as well. Okay, you should know that as well. So next, I will explain how do you use this model in practice? Okay, then the first question you will ask me will be, okay, where do I get sigma t? Okay, I know where do I get RT because I can read it from the market. So where do I get R sigma t? Okay, what is sigma t? Sigma t is basically the forecast for today's volatility you made at end of yesterday. Okay, and basically sigma t, based on the risk matrix model, sigma t is going to be 94 sigma t minus 1 squared plus 6% of RT minus 1 squared. Okay, you basically write the risk matrix model one period backward, you get the sigma t information. Okay, that's the forecast you made regarding today's market volatility based on the information up until the end of yesterday. Okay, and then if you go one period backward, okay, where do you get sigma t minus 1? You know, you're gonna rewrite this one period back again, okay? So basically, you can do this, okay, recursively backward, okay, until sigma 1 squared equal to 94% of sigma 0 squared plus 6% of R. Oh, there's no R0. So let's write this way. So you can do sigma 2 squared. Sigma 2 squared equal to 94% of sigma 1 squared and 6% of R1 squared. Okay? So basically you rewrite this risk matrix model backward, okay? And then you end up getting this. So this is where, unless you know what is sigma 1, you can start the iteration, right? You know sigma 1, you plug this into this equation, you know what is R1, you get sigma 2. Then you can get sigma 3, sigma 4, sigma 5, until sigma t plus 1. Okay? So therefore, an important choice you gotta make is, what is sigma 1? Okay, what is sigma 1? So you can see on the slide, it tells you that on the first day of the sample, the volatility can be set to the sample variance of the historical data. Okay, basically, you can just choose the average level of the volatility to start using the risk matrix model. For example, we know that for S&P 500, the daily volatility is about 1.37%. Okay, you can just use that number to start the iteration to use the risk matrix model. But what I'm going to show you that is, okay, so that initial value you use at the beginning of the risk matrix model doesn't matter for the volatility dynamics today. Okay, so basically the impact of the initial value will quickly die out in a few periods. Okay, let me show you that. So any questions with the exercise I'm just showing you here? So basically, what is the risk matrix model and what is used for, and also how to use it? So regarding the three questions I just asked, any questions do you have? I'm basically going over the three questions, okay? So what is the model, okay? What is it used for? And then how to use it? Okay, and if we are all clear, I'm going to show you how to use it in R, okay, in R. So let's close this. Okay, the code is in the lecture 2 folder. Okay, if you go to your Husky CT and in the lecture 2 folder, there is VAR. Okay, there is a VAR file. Okay, let me open it. Change directory to the lecture 2 folder on the desktop. Then let me open the VAR codes. Okay, so the VAR code is open, and then you can see right away that the upper portion of the code is the same as the one in the previous code. And basically this portion of the code is what I'm using to get the data from that CSV file and calculating the log return and remove the trading holidays, basically clean up the data, okay? And the IET is going to be the time series we are going to be working with to illustrate the use of the risk matrix model. So you can see the next part is how I use the risk matrix model. Okay, how I use the risk matrix model. So let's take a look at a very simple example. Okay, so the first thing I'm doing is I create a variable called sigma 2. Sigma 2. That's basically sigma square. Okay, I'm basically creating a variable called sigma square. And the numeric t, what is t? I should have used n. Okay, t is a little bit confusing. Let me change this to n, because t means the true. Okay, so but if you use this, it can still run. Okay, I just wanted to make sure there is less confusion for you guys. Let's use n here. Okay, so basically n here is the length of the data. Okay, and then if you create a vector numeric n, okay, numeric something, let's say numeric 5, what it does. Okay, numeric something is basically help you create, okay, a numeric vector with all the elements being 0. Okay, with all the elements being 0. So why do I do that? Because I wanted to estimate or forecast a volatility for every day in the sample. So therefore, I will pre-create. Okay, I will create a variable ahead of doing the code to save all the volatility. I'm putting all the volatility to be 0 to begin with. Okay, to begin with, and then I will be after every day after I estimated a value, I will put it back into this vector. Okay. And then you can see that for the first day, I assign a value that is 1.4% squared. The 1.4% is basically the unconditional volatility for the S&P 500 during this 10-year period. Okay, and then you can see I'm taking a square. That's going to be the first element of the sigma square. Okay. So, and then the next thing I'm going to be doing is I'm going to do this loop. Okay, I'm going to do this iterative procedure. In all the programming languages, if you want to do something in a very kind of similar fashion, basically every step of the way you are doing something similar, you want to use some tool called a loop. Okay, a loop. Basically meaning every day you just have to change the timing. Okay, and the work is being done within the loop is basically the same. Okay, basically every day we are using the information, we are combining two pieces of information. One piece is volatility, the other piece is the return. We're combining them, have a weighted average to come up with the forecast of the volatility for tomorrow. So therefore, I can use the for loop. Okay, so this is the first loop we are using in this course. So therefore, let me explain it. Okay, so when you are using the for loop, you always want to write for, okay, and then you put the indicator, because for the loop, okay, you always have to tell, at which location you are currently working on, okay. So basically, we are going to start from day 2, okay. So therefore, the I here is the indicator, tells you the location or the time you're working at, and then the in 2 until t, meaning the first location we are going to be working at is day 2. Okay, until day t, actually this should be n. I will change this to n, very soon. And then for I equal to 2, the sigma square at day 2. Okay, you can take the I to be 2 first. Okay, because we are going to start from day 2. So sigma square at day 2 equal to 94% times, this is times. Okay, sigma square at day, when I is equal to 2, this is going to be 1, meaning sigma square at day 1. Okay, that's already assigned and given to you. Okay, plus 6% of the return square at day 1. Okay, that's exactly this formula. Okay, sigma square at day 2 equal to 94% of sigma square at day 1 plus return square at day 1. Okay, then you will be able to get the sigma square at day 2. Then when you are out of the loop, you move I from 2 to 3. Then you can estimate sigma square at day 3 equal to 94% of sigma square at day 2 plus 6% of return square at day 2. Okay, you can see the for loop is basically can help you do this iterative procedure, okay, in a very quick way. okay, in very quick way. So let's quickly run this command. Okay, let's run this command.
Professor,
Oh,
can you explain again the 0.014? On the
94. Where is
the
14? The initial value. Okay, this is the. Remember that for you to start the iteration, you have to at least assign a value for the first day, right?
Yeah.
So for the first day, what we typically do is we assign the average of unconditional volatility for that period. Okay, remember for the 10-year period, we know S&P 500 volatility is about 1.3, 1.4%, right? Take a look at this. 1.4%. Okay, we are basically. I'm not kind of putting an exact value there because this value I will show you very soon that value doesn't matter much. Okay, so right now let's put 1.4% there. Okay, and then let's take a look at the estimated sigma square. Okay, you can see this is very quickly down. Okay, very quickly down. And then I'm going to plot a time series, okay, because the sigma square here is still a sigma in the volatility square. So if I wanted to plot volatility, I need to take the square root of that sigma square, okay? So you can see what I'm plotting here is SQRT. SQRT means the square root of something, okay? So this, by plotting the square root of the sigma square, I'm effectively plotting sigma, the volatility time series. Okay, let's take a look at it. So this is exactly the time series during the 10-year period. Okay, and how do we interpret it? So basically, the high value meaning more volatile market. Okay, and you can see the interpretation is very straightforward. It's actually exactly consistent with our perception of the market. Okay, so basically, you remember 250 corresponds to 1 year, right? So basically, this is 2001, this is 2002, this is 2003, this is 2004, 2005, 6, 7, 8. Okay, and then 9, 10. Okay, so you quickly know that the spike, okay, the highest level of the volatility happening at the somewhere around the end of 2008, maybe in the fall of 2008. Okay, so that's basically at the height of the financial crisis. So roughly around the collapse of around the bankruptcy of the Lehman Brothers. That's when the market was the most volatile. Okay, so basically that corresponds to, so this spike in volatility corresponds to the global financial crisis. And the smaller spike here basically corresponds to the dot bubble period. Okay, and then in the middle from 2003 to 2007, we have 4 years of low volatility, or in other words, relatively calm market. Okay, relatively calm market. And so this is basically the resulted time series forecasted by using the risk matrix model. You can see a very simple model give us something that is very meaningful. Okay, basically we have a time series for volatility forecasted by using the market data. Okay, then the next question I wanted to explain to you guys is the value you use at day 1. It doesn't matter much, okay? Because at the end of the day, the volatility is driven by return dynamics, okay? As long as you are using the same return time series, the volatility will be very, very similar. Okay, the impact of the initial value will only matter for the first couple of periods. Okay, let's quickly test that idea. Okay, so basically in the second part of the exercise, okay, what I'm doing here is I'm going to do a very simple exercise. I'm going to ask the question of how much does the initial value matter in the risk matrix model. Okay, I'm playing with 3 time series. Okay, ABC. Okay, the time series, they're only different in the initial value you are using. You can see for the A time series, I didn't even reassign value for, meaning the initial value is actually 0. Okay. Then for the time series B, the initial value is 1.4%. That's exactly the default version we just played with. Okay. Then for the C time series, the initial value is 5%. That's a pretty big number. Okay. And then I'm basically re-estimating the risk matrix model. Basically, it's copy and pasting the code from there. Basically, for 3 different time series A, B, C. Okay. You can see the A, B, C time series, they're only different in terms of the initial value you are using. And then toward the very end, I'm plotting the 3 time series all together. Okay. And you can see plot time series A, point time series B, point time series C, and the difference between plot and point is that plot is going to make a new plot, okay, and point is going to add a line to an existing plot. Okay, so basically I'm going to add the time series B and C to that existing plot to contrast. Okay, and you can see the 3 lines are going to be kind of differentiated by 3 colors. Okay, the A line is black color, B line is blue color, C line is red color. Okay.
So when you did the original preliminary code,
version.
do you need version? You did sigma 2 numeric, you changed it from Y to N for convenience, and then you did numeric 5. In order for this to work, do you need to have that where if it comes out blue, 1 0 0 0 0 0? Does that have to populate first in R for this to work?
Oh, okay, good question. Basically,
Is
you're
this in a sequence?
asking why do we have the 3 lines here, right?
If this is in a sequence after that has already been done, correct?
You mean a sequence of already been done there?
You didn't put this into R yet. Everything is highlighted.
This highlighted portion, not yet.
Right, I'm saying that has to be done. This won't work without you having done that, correct?
No, this will always work because the ABC here, the new variable being defined. Okay, the variable here is sigma square. There's no kind of underscore A there. So did I understand your question?
I'll just wait to see how it goes.
Okay. So basically, I'm gonna run this code. Okay, I'm gonna run this code. The end result, I'm going to be plotting the 3 lines all together, and they are going to be differentiated by different colors, and then you will be able to tell. Okay, you can see that the 3 lines are actually plotted all together on this graph, but you can only see the right line. Okay, you can only see the right line during most of the time. The reason is because the 3 lines actually overlap most of the time during the horizon. Okay, and that's why you don't see other colors, but you only see the different colors at the very beginning of the horizon. Okay, you can see the black color, the blue color, the red color. Okay, because you are using different initial values. Therefore, initially, the forecasted volatility or variance, they are different. But gradually, after a few periods, the impact of that initial value dies out. Okay, so basically, at the end of the day, the volatility, so only the return dynamics matter for the volatility. That initial value itself doesn't matter. Okay, so that's why the initial value you are using there doesn't really matter. Maybe an initial value you are using to start the risk matrix model doesn't matter for your volatility forecast maybe 50 days later or 100 days later. Okay, so therefore you can choose the value of your own preference. Okay, you can choose any value you like to use. Okay, so this is basically the objective of this exercise. I wanted to show you that you do need an initial value, but that initial value impact is very short-lived. Okay, it will die out very soon. So therefore, for forecasting volatility using the risk matrix model, you can choose any value that you like.
This is because the time series we chose is long enough, right? Like 10 years is long enough.
Oh well, I would say even beyond 3 months, it won't matter. You can see the difference is only lasted for maybe 100 days, maybe 100 days. 100 days is 5 months, right? 5 months, because every month is about 22 daily observations. Okay, 100 basically meaning 5 days. Basically, the impact of that will go away in about a couple of months. Okay, so therefore you can use anything that you like to use. Okay, and I think one question he was asking was, why do we want to, when we are using the risk matrix model, why do we want to pre-specify a vector to see the estimated or forecasted volatility? Okay, so actually you don't have to do it. Actually, you don't have to have that step. So the reason why I'm putting that basic to help, this is, because we're doing programming, right? So we wanted to develop good habit, okay, for programming, because programming can be done in a variety of ways. Some codes, they are more efficient in terms of, occupying the computer memory, using the computational capacity, okay. Some codes, they are taking longer to run, okay. I think over time, when we are doing more and more coding, we want to develop better habits to make more efficient code. So this is one basically example of how do you make your code more efficient, because for loop, we are going, for every step of the way, we are going to create a forecast of that sigma. Okay, so basically, if you don't pre-specify or pre-create a variable to save all the potential future forecasts, then when you are doing the for loop, that vector will change inside every step of the way. It's gonna change from one vector to like a 2-element vector, 3 elements, 4 elements. Okay, so basically the memory space being used in your computer, you're gonna change it dynamically from small to big. Okay, that's gonna actually use a lot of memory, because the computers, they will not delete the old memory that fast. Okay, so basically when you are replacing the variables, the memory is still being occupied. So therefore, to save computer memories, okay, so we are creating this variable. Once you create this variable, the memory is already kind of allocated. So therefore, in the future, when you are reassigning values, the memory side will not change. It's just like the elements in the vector will change. Okay, that's basically gonna make your code a lot more efficient. Okay, so overall, I think in the future you will realize that when you are dealing with larger data, R is actually more memory constrained. Okay, so sometimes it cannot use all of your computer memory. So therefore, you gotta be careful in terms of kind of allocating the memories along the way. Okay, so that is the risk matrix model, and how do you use the risk matrix model?
Question: is it garbage collected language?
What?
Is R a automatically garbage collected language?
Garbage collected language.
Anyway, I will search.
So, okay, so basically we talked about the risk matrix model. Okay, we also talked about how to use the risk matrix model. So we have a few minutes left. I will quickly talk about the concept, okay, and then I will let you guys go. Okay, so a concept that is actually very familiar to you guys, but it is potentially defined in a different way in this course. So it's the value at the risk. Okay, it's the value at the risk. Okay, so you guys all know this is a very popularly used risk concept. Okay, especially for the risk management, applications. Okay, and oftentimes we use VAR to denote it. We use VAR to denote it. So, and this is a risk measure. Okay, and for a risk measure, we oftentimes want it to be a strictly positive measure. Okay, why do we want it that way? Because if that risk measure is always positive, basically meaning larger number, meaning higher risk, okay, it's much easier to interpret, okay. Unlike returns can be negative, could be positive, but for risk measure, we want it to be always positive, okay. I hope you guys keep that in mind, okay. So before I talk about VAR, I wanted to introduce another concept that is more like a statistical concept, okay. It's a concept called quantile. Okay, anyone know what a quantile is? Okay, no idea what this is. Okay, this is basically a statistical concept related to the cutoff on a variable distribution. Okay, you guys, if you haven't heard about quantile, you must have heard about different examples of a quantile. For example, you probably have heard about median. Okay, you probably have heard about quartile. Okay, you probably have heard about percentile. Okay,
Yes.
all of those are examples of quantile or special cases of quantile. So let me first highlight or explain what is quantile. Okay, what is quantile? So basically, you have a histogram of a particular variable. Okay. Okay, so the histogram looks like this. Okay. It doesn't look like exactly normally distributed, but you have a lot of observations in the middle, okay, and then you have some observations at both sides of the distribution. So let me explain what is a quantile, okay? So oftentimes when we talk about quantile, we always associated quantile with a certain probability. For example, we're gonna be talking about 1% quantile. Okay, what is 1% quantile? It's basically a cutoff level on this histogram. So the cutoff is basically here, okay? A cutoff level on this histogram such that the lower values on this distribution, on this histogram, is happening with a probability of 1%. That's gonna be called the 1% quantile. Similarly, 5% quantile is going to be here, okay? It's basically a cutoff on this histogram such that lower values than this cutoff is happening with a 5% chance, okay? So this is basically what is meant by quantile, okay? You can see it's actually strictly a statistical concept that is related to a variable's distribution. Okay, it tells you, how do you think about the distribution of the observations of a particular variable. Okay, so then why do I see, median is a special case of quantile? Median is basically, okay, middle range of the value, right? Such that lower and above, they are both 50%. So basically the median is equal to 50% quantile. So basically median is a special case of a quantile. It's exactly 50% quantile. And the first quantile, that's gonna be equal to, or it is defined as the 25% quantile. Okay, of course, the second quantile is the median, right? The third quantile is 75% quantile. Okay, percentile is also a special case of the quantile. Basically, the first percentile is basically the 1% quantile. Okay? Okay, so why do I introduce this concept to you guys? Because in this course, the VAR, the VAR is a concept that is very closely related to quantile. Okay, VAR is a concept that is very closely related to quantile. So VAR is also concerned about the distribution, especially at the left end of returns or portfolio gains or losses, okay? And it's concerned with, how many percentages are going to be fall under this region, Okay, but the only difference between var and quantile is that you can see that quantile is a cutoff here, right? If the mean of this distribution is roughly 0, and this cutoff is going to be a negative number, right? But for var, we want it to be defined always as a positive number, and that is why the var is actually going to be equal to negative of the quantile. So if you put a negative sign in front of the var, you get the you put a negative sign in front of the quantile, you get the var. Okay, the good news is that for both var and quantile, when you talk about them, you always associate them with a certain probability. For example, the 1% var, okay, is equal to the negative of the 1% quantile. Okay, and we do have a name for this 1% for in the case of var. Okay, the 1% is oftentimes called the coverage rate of the var. Okay, coverage rate of the var. Okay, so now given the close relation between var and quantile, you guys probably know how do I figure out var. Okay, how do I figure out var? So basically, let's say if this is the return distribution or the return histogram, so how do you figure out var? All you need to do is figure out or find out the quantile and then put a negative sign in front of it. Then you have the var. Okay, so then your job is to find out what is the 1% quantile of the return distribution. All you need to do is find out, okay, what is the cutoff level such that the lower return is happening with a 1% chance? Okay, so the good news is that in R, okay, we do have very handy function that can help us estimate the quantile of any variable. So therefore, to estimate var, you just have to use the quantile function. But you always have to keep in mind the difference between var and quantile. Okay, the difference between them is the sign. Okay, var have to be always positive because it's a risk measure, and the quantile can be negative, can be positive. So therefore, for the var, we wanted to put a negative sign in front of it to get the var. Okay, any questions with this kind of relation between them? So the next thing I wanted to very quickly related to the var concept. Okay, I think you guys have already learned about it from other courses. Okay, but my expectation for you guys is if I give you a particular var statement, okay, you should be able to interpret what that means. Okay, so for example, if I give you a var statement like the 1% var of S&P 500 in October 19th of 2008, okay, if the 1% var is 13%, how to interpret that? Okay, how to interpret this statement? Okay, this is very important because that shows you how deeply you understand what var is, or how deeply you understand this risk measure. Okay, so my trick for doing the interpretation is you translate this statement to quantile. Okay, given the close relation between var and quantile, you first translate this. Basically, it tells you that the 1% quantile of S&P 500, okay, is negative 13%. Okay, and then you go back to this histogram, and you know that, okay, if the cutoff here is negative 13%, it means that on that particular day, there is a 1% chance the return will be smaller than negative 13%. Okay, that basically shows you how severe the market was at that point. Basically, a 13% VAR is already a very high risk situation or high risk scenario. Okay, that is highlighted by this particular statement. So there is a 1% chance your return on that day will be even more negative than negative 13%. You have a question?
Yeah, you stated that VAR is always positive, right?
Yeah,
And but VAR is negative or quintile, right?
yeah.
So and you said quintile can also be positive or negative.
Uh-huh.
So
What if quantile is positive, right?
oh, is that? Yeah, what if it's positive?
Okay,
So
okay, that's a very good question. So basically, when we talk about risk management, okay, so we are more concerned with the left end of the distribution. So basically, if this is the returns, okay, if this is the return distribution, of course we are worried about when return is negative. Okay, we are not worried about when return is positive. So therefore, the VAR we are talking about is oftentimes like 1% VAR, 5% VAR, 10% VAR. Okay, they are all on this end of the distribution. So therefore, the quantiles are all negative. So when you are putting a negative sign in front of it, it's gonna become positive.
So if the quintile is negative, so the VAR will equal to that negative number, right?
Yes, so technically
have to
yes, but it
interject
won't
anything.
happen. It won't happen in practice.
Oh, okay. So
Yeah.
we won't have to interject or anything with it.
Right, you don't have to anticipate that happening.
Oh, okay.
Okay, so we'll stop here, and then next Tuesday we'll continue talking about methods to estimate VAR. Okay, so okay, see you guys next week.
Thank you.
I do apologize. Do you have a list of